Hello, my name is Moyed Hajali and I'll present to you VidStyleODE, a principled method for performing various applications in video editing by disentangling appearance from motion with the help of a pre-trained image generator and neural ordinary differential equations. This work was done in collaboration with Andrew Pond, Tolga Berdal, Levent Karajan, Dogi Jaylan, Erkut Erdem, and Aykut Erdem. Given an input driving video, our method is able to animate a static image with the motion from the driving video, change the appearance or motion of an input video, or change the motion of a single body part, where the motion of that part is copied from another co-driving video, while keeping the rest of the motion similar to the first driving video. VidStyleODE also enables temporal interpolation and extrapolation. Now I'll discuss the model architecture and training objectives. Given an input video of k-frames, our method first encodes the content of the video into a global code using a pre-trained inversion network. Then we encode the dynamics of the input video into a motion latent representation. For an arbitrary sample timestamp, we are able to sample the structure of the target frame using the motion representation. We then use a modulation network that modulates the target structure over the global code, and an additional input condition that specifies the target edit. The modulation network then produces a new latent representation ZNU that is passed to a pre-trained image generator to produce the output frame at time t. To obtain the global code, we invert all of the frames of the input video into the StyleGAN W+ space and take their mean as the global content code ZC. To extract the motion representation, we first encode the structure of each input frame with a convnet. Then we use a comGRU module to aggregate the frame representations into a single motion representation ZD0. This representation is used to initialize a latent ODE that models the change in the structure of the input video, so that we can compute the structure representation of any timestamp t. To model the target appearance change, we obtain the representation of the target frame in the clip latent space by encoding a sampled frame from the input video xi with a clip image encoder. We then add to it the direction in the clip space between the target and source description multiplied by a parameter alpha. For the modulation net, we first process the sample structure with a self-attention layer by tokenizing the structure representation. We then use a cross-attention layer between the output of the self-attention and the representation of the target frame in the clip space. This is then passed into an adaptive instance normalization layer that produces a direction in the W+ space. We add this direction to the global code to obtain a latent representation of the target frame ZNU, which is passed to the pre-trained image generator to decode the target frame. Here, we show a sample of manipulating the crop top into a plus. Hair clip produces a highly inconsistent color and style due to applying different directions in different frames. Stitch It in Time is able to reconstruct the identity of the input video because of its test time fine-tuning, but fails to realize the target edit or keep the high-frequency details. DCOMOGAN is limited to low-resolution videos and generate many artifacts. Our method is the only one that produces realistic and temporally consistent manipulations. We omit StyleGAN V as the model didn't converge on this dataset. We observe similar issues with the baselines on this dataset. Stitch It in Time loses high-frequency details, and Hair Clip produces inconsistent appearance. StyleGAN V is also unable to reconstruct the dynamics of the input video. Here we show that our method is able to perform complex text-guided appearance manipulation in a consistent manner, such as the garment color or length, while keeping the motion of the input video intact. We compare our method performance in image animation with motion representation for articulated animation and StyleGAN V. StyleGAN V is unable to handle the complexity of full-body videos, and MRAA is unable to keep the clothing style and identity of the reference image. Here we show that our method is able to animate the reference image into a different set of motion. We observe a spatial correspondence between the motion representation and the input video. This allows us to copy the motion of a specific body part by blending the motion representation of two driving videos. Here, in the third column, we copy the leg motion of the second driving video while keeping the upper body motion the same as the first column. In the fourth column, we copy the upper body motion while keeping the legs motion the same. Here we show that our method is able to interpolate between frames in a realistic way. Our method is also able to extrapolate from a single input frame. Thank you very much for your attention, and please visit our project webpage for more details.